My name's Ty. Let's get started. So when Uber was a much younger company than it is today, the mobile team was just a small group of engineers, and it was pretty easy for them to talk to each other, work with each other, and share knowledge back and forth. And the team could build, a single app in one small repo using the state-of-the-art tooling at the time, like Ant and Eclipse. And that app was really small with a really tight focus, just a good MVP. And that team very quickly grew alongside the business, going from one Android team to multiple teams, including a platform team with multiple vertical program teams building features on top of that. And the team thought it was important to address this scale and what they expected to continue, so they standardized around an MVC architecture and used modern tooling for the time. These components were really well composed. They allowed new engineers to develop pretty well against the solid principles. And over time, that app became multiple apps split across different repos. And so common code was extracted out to create shared libraries that both the apps could use as a dependency. And that common code was modularized into multiple core library repos that were consumed as versioned Maven dependencies. And with new contributors and a good foundation, they could scale and launch new product offerings. And that organic growth became pretty massive. Literally hundreds of mobile engineers joined the company to contribute to just a small number of applications. New pain points emerged regularly. Tribal knowledge started falling short. It was hard to communicate, and the organization just slowed down. And so many more controllers were added to that architecture. And that caused bottlenecks to start to emerge, where some areas became bloated with scoped objects on the graph. They would be coupled to more downstream dependencies, creating a large number of unmaintainable classes. And that iteration process slowed down to a crawl, requiring updates of downstream dependencies, multiple sequential CI jobs, and then updates to multiple top-level apps. Developer productivity took a large hit, and architectural silos emerged. And the product choices continued to follow that organic growth model, essentially creating a kitchen sink of products for the end user with little focus on usability. The number of product choices in the bottom sheet of the Uber app became a joke to many. So at this point in 2016, we knew that growth couldn't continue unchecked, and that scale had to be planned for. So at this crossroads, Uber rewrote and redesigned the Rider app. And at the same time, they wanted to create a product that could be built on for years to come without the same sort of constraints. So this talk today is going to cover a bit about that approach, about opinionated scaling, and then the tools and processes that we've used to facilitate that, and that we've open sourced so that you could potentially use for your application as well without over-engineering. So today, I want to talk about a few major areas of scale. And we've made some headway against all of these, but I wouldn't call these solved. First, we'll discuss our project structure and build needs. And then we'll talk about RIBs, which is our architecture solution and the backbone of our modern apps. And finally, I'll discuss some libraries and tools that we've used to facilitate faster mobile development. This will in no way be an exhaustive list. If it was going to be, I'd be here all day. This is going to be a pretty high-level overview of a lot of these libraries. And then I'll cover resources and links and other talks at the end that I can send your way so that you can go follow up for more information. I'm also not recommending that you use all of these. These fit very specific needs, and I would recommend that you be very intentional with your scaling thoughts and you use what's appropriate. You may have noticed in my first slide that we more or less started with a single repo and then split it out into multiple repos as we scaled up into multiple apps and multiple libraries. Like many other companies, at the scale of our mobile development, we eventually had to consider the trade-offs of staying in a multi-repo world versus merging everything back into a single repo, canonically known as a monorepo. Many of the developer productivity issues we were experiencing could be pinpointed back down to having to work across a lot of different repositories. The three major pain points we were feeling were issues with transitive dependencies, with updates being required in multiple repos and then duplication of effort. The emergence of multiple layers of architectures and conflicts amongst different projects as teams worked in more isolation from each other. and long build times, as the build system was really inefficient at parsing and building sub-modularized code bases. To demonstrate a problem in a multi-repo world, let's assume that we have an app with a chain of transitive dependencies. If an API breaking change is made downstream, an update will need to be made in each of the libraries in the chain, with a commit, waiting on the CI builds, waiting on a deploy to Artifactory, before finally moving on to the next one in the chain. Clearly, this is inefficient, and this assumes the best case scenario where all of these are updated properly. But a more common situation is where we have two build scripts for an app and a library that the app uses. As you'll notice, we declare a number of fundamental libraries here in the build scripts for these two different apps, like storage and networking. And these have certain versions. And you'll immediately start to see that there's some oddities that are emerging. Gradle, specifically, the version numbers between some of these differ. Now, Gradle will try to resolve the version conflict by default choosing the highest version. So if a API change was made and there is a library that's transitively depending on an old version of the library, we aren't guaranteed what that behavior will be when it is instead forced to use the new version of the library. So these pain points drove our decision to move from a series of multiple repos to one large monorepo per platform. This new project layout gives us the ability to update across multiple modules in one atomic commit, and increases developer productivity significantly. For example, here'd be a similar example to the mini repo one I gave a moment ago. But here we guarantee that all our downstream dependencies are pointing to the same version. In addition to our project structure, to maximize the gains for our developers, our DevX team, Developer Experience, invested heavily in converting from Gradle to Buck. While Gradle has made tremendous gains in performance over the last couple years, for a large code base like ours at over 1,000 modules, Buck still has better performance and better fine-tuning. And if you're not familiar with Buck, it was built by Facebook, and it follows a similar architectural pattern to Bazel, Google's monorepo build system. Its build architecture is based on cacheable outputs. Buck encourages many small modules, and it's highly parallelizable. If your project is efficiently architected, it will use all the CPU cores on your machine. I've definitely been trying to stream music and seen that stutter just doing a build. Because it's so parallelizable, it can cache outputs on the very small modules. And that makes it very fast to use. And if you use something like Buck's network cache, then those can be shared across all of the teammates that you have working on a code base, and it's going to be even faster. Buck also has pretty good IntelliJ integration to keep a productive workflow, including concepts like building, deploying, running tests, and using unloaded modules for large projects by generating just the IML files for the specific things that you're trying to work with in your IntelliJ workspace. Buck is a lot more focused than Gradle, though. So you can attain greater speeds, but it's much less flexible overall than Gradle. It's also notoriously more obnoxious to configure its build scripts. Because of this, I say Buck is kind of like rocket skates. You can go really fast, but you don't want to change direction or fall over. So to address some of the hard-to-configure build scripts and lack of features like dependency management that Buck has, we built an open source project called OKBuck. And it's a Gradle plugin that you can add to your Gradle project like any other. And then you can execute a Gradle task to generate a Buck wrapper object. This will configure your project and create Buck config scripts per module, eliminating the need for you to manually write your Buck config. Running the Buck wrapper has multiple advantages. It downloads and installs and updates Buck so you're on the right version. It has minimal overhead to decide when to run OKBuck, since that is a slower task and does need to spin up Gradle, which does its configuration stage and all that. It also handles gracefully the cases when the OKBuck task fails or is stopped abruptly. And the speed of Buck in a hyper-modularized code base is great, and this kind of gives you that, while giving you more of the simplicity and features of Gradle like dependency management. So this has worked pretty well for us so far. Another pretty cool feature using Buck is called exopackage. Now, exopackage constructs a shell application where each module's dex files can be hot swapped out. So this allows much smaller changes to be deployed to the device in a much faster way. It's similar to Instant Run, but it actually works. Here on the first run, the APK builder will construct an entire shell app, and it'll install all of the DEX files across. And then on subsequent compiles, it'll only send the changed DEX files across the wire. So we found that in larger applications like the Uber Rider app, this can save up to 30 seconds on USB transfer time. The last helpful build tool I want to cover solves a problem that I'm sure some of you have experienced at some point. But as you get more developers contributing to your code base, it becomes a lot more common that master breaks frequently. So people step on each other's toes, merge conflicts come out. And oftentimes, as you have more engineers, these happen in between CI jobs succeeding. So with hundreds of mobile contributors, we were in a state last year where at least once per day master was broken. And when this would happen, it would take a while to get it resolved, and engineers would just be thrashed. Developers would get pulled, they'd rebase their change, it'd immediately start breaking. They wouldn't know if it was their change that was causing it, if it was something they pulled down. We saw that productivity just took a huge hit. So we introduced a concept called submit queue. It's not a new concept. It gives us the power to validate that a diff will merge successfully against master, and it'll batch jobs and run. So this is a job that runs after all of the CI verification has been done. A developer's ready to land this on master, and then they submit it. It runs these verification jobs. This has helped us keep our master branch green and developers much more productive. This has been implemented by a lot of different companies, different projects. If you're looking for a good open source implementation of this, the Kubernetes project is running this in their open source repos, and it works pretty well. So with our project structure defined, compiling and sailing smoothly, it's time to move into how we're actually building the applications. So in early 2016, we took a small group of our platform engineers and charged them with researching and creating an architecture that we thought we could build on for all of our apps that would work for the next few years. They researched a lot of the existing architecture solutions and eventually proposed, we came up with our own. We codenamed that Presidio, and it would become the foundation of many of our modern apps today. There were a number of goals stated with this architecture project. We wanted to define the difference between core code in our app that's required for the user to complete what we consider the critical path, and then optional features that could be spared to be turned off if there was an issue with reliability. And with the scale only expected to increase, with Uber growing as a business, hiring new folks, and new product lines coming on, we wanted to set up a foundation for applications that would last for years. We wanted to create guidelines and rails for our developers and for our designers so that they could work in a fast, consistent, and reusable way across all of our applications. And you can't really define success without being able to measure it properly, and we didn't want to leave that up to each individual team to come up with their own requirements for measurements and success. So our foundation should provide that as a first-class citizen. Users rely on our application as a daily utility to their lives. People use it for commuting to work. People use it sometimes in the event of medical emergencies. And to move fast as a company, the people can't be afraid of breaking the product or the application. So the foundation needs to provide the basis of experimentation so we can move quickly without worry. Lastly, our tools should empower, not inhibit, a great app experience. It should be performant and handle things like degradation on low-end devices out of the box. So based on those architectural goals, we investigated well-established architectures like MVC, MVVM, and Viper. We found that each had its downsides. MVC and MVVM commonly has hard-to-maintain fat view controllers. Our old Rider app was built in an MVC architecture, and classes like our ride request class started with 300 lines of code. They were very maintainable, and very quickly they ballooned to over 3,000 lines. They became very fragile. Testing was difficult, and updates slowed down for teams. We liked a lot of things about Viper, including its more explicit separation of concerns, easier testability. However, using a pure implementation of Viper would require us to couple the application state to the view tree and leak business logic through the presenter, so that was something we weren't super excited about. So based on those principles and the inspiration from Viper, We created an open source to cross-platform architecture and framework called RIBS. It's implemented natively on Android and iOS. You can see both of those in the GitHub repo. But the domain language is shared across both. So you can have your mobile engineers on both teams talking about common patterns that can be used on both. Helps improve collaboration and design and the like. So a RIB unit is defined by a builder, which creates the other components of the RIB, an interactor to manage the business logic, a router to help with routing between the different RIBs. And since we wanted the application state tree to be tied to business logic, not to the view tree, RIBS encompasses an optional view and presenter to manage the data model, translations, layouts, animations, and eventually presenting those on the screen. Our writer application is then represented in business logic by state trees, where each node is a RIB unit. Each one of these can be instantiated, attached, detached, and active when needed. So let's walk through an active RIB tree while the user is requesting a ride to kind of give a little bit of context. So initially, the app starts up. Only the RIBs related to the home screen would be active for the user. These are in memory. These are active. The user's interacting with the screens that are being displayed. As the user moves through the car request flow, confirming their ride, the home RIBs are detached, and a confirmation RIB is attached in its place. Followed by a refinement choice where the user can confirm that the spot that's being picked up is the right place. Maybe they can move the GPS pin a little bit. And finally, all pre-trip related RIBs are detached, and an on-trip branch is created and attached. Communication between RIBs was designed to satisfy the open-closed principle. For communication downwards, we rely heavily on Rx. A stream is placed on the DI graph by a parent RIB, and an emission is made from that stream to be consumed. And for communication upwards, the child RIBs would define an interface that the parent would implement, and then the child would execute that as needed. With the backbone of our app defined, I want to walk you through some of the tooling and libraries that we use both to support RIBs as well as generally empower better mobile development at scale. To help developers using RIBs, we wanted to reduce the boilerplate required to create them. When you're using very verbose architectures, they inherently come with more boilerplate. So we created an IntelliJ plugin that'll auto-generate base RIB units. And so this will do all the required classes, the Dagger components, interactor, builder, router, all that sort of stuff, and then wire up the components for you. This is a part of the open source project, so you can see this in the main RIBs repo. One of the bigger complaints that we've gotten from our many Android developers at Uber, and we pretty frequently hear this from our peers at other big companies, is that Dagger has a pretty high learning curve, and it's really complex in a large code base, especially when you have a lot of really deeply nested scopes that are pretty granular. Tasks like wiring up dependencies down from a parent component when the nested when subcomponents won't scale out, the boilerplate of wiring up the nested components to themselves, and the debugging when a dependency related build failure was missed are all some of the common complaints that we hear. So we built an open source library called Motif to solve this. We open sourced this a few months ago. It's still mostly being developed, but we're in the middle of migrating a lot of our applications to use this. So it's pretty stable at this point. So this is a code generator for DI that sits on top of Dagger. So this is generating Dagger under the hood. And it provides full interop with Dagger. But it gives a much simpler subset of Dagger's APIs, and it's much more explicit about their use case. So we find in practice this reduces a lot of the concepts that a developer has to be concerned about in a deeply nested architecture, while maintaining the full flexibility of Dagger when that's needed. So we can walk through a short example of this. Here I've defined a very basic scope using the @motif.scope annotation on an interface that will serve as the container for objects and that can be created by the scope. We can then explicitly declare a child scoped interface that will generate the appropriate bindings in Dagger. We then annotate a factory class with the Motif objects annotation to provide our dependencies. And we can explicitly declare which of these is exposed to our children. And that's all you need for basic wiring of a top-level scope. Now in our child scope, we're able to use that database dependency provided by the parent. This project isn't designed to replace Dagger, but it works well when the architecture suits it. And through our ID integration via plugin, exploring your DI graph and debugging missing dependencies on it becomes much more simplified. There are a lot more features to this. Check out the repo that I have linked on the bottom of all of these to get more information or to get involved in collaborating or contributing. One of the most important pieces of functionality that was built into the new Rider and Drivers apps was the ability to distinguish between what we consider core code, which is critical to the user, and then optional code that's backed by a plugin system so that we can enable safe rails for developers to build on and turn off functionality remotely when it's inhibiting users. And we somewhat recently built an open sourced metadata generation tool called Crumb, evolved from an internal project called Synapse, that can serve as the backbone of this type of functionality, or just generally generating metadata that can be viewed across the compilation boundaries. So it enables you to generate metadata in a downstream dependency, and that can act as providers of information in upstream parents that can be consumed. So we combine this with a tool like Java Poet or Kotlin Poet to generate code on both sides based on this metadata. So in this diagram taken from the example in our public repo, you could see how a plugin system for collecting dictionary translation implementations as plugins defined in libraries could be managed across compilation through like a library that might be providing them, and then an application that is needing to display. In Crumb's repo, you can see the full code example of this. It's pretty verbose, and dealing with code gen is never an easy task, but this simplifies this use case. In our apps, though, we have a lot more complexity to this than the simple version that we have in Crumb's open source repo. And so we've built something similar on top of our A/B testing backend service. Now, this allows the rollout of new features behind a plugin. And in the event of a crash or an outage, when we see regressions, we can roll these back, or we can turn them off in the wild without having to do a hotfix. So here's your typical plugin. It contains an identifier that can be referenced against a copy of our cached experiments that are pulled down from the network. And so this is the information that's used to determine if it's applicable for the dependency to be provided. And this allows it to create the underlying plugin. We then provide a plugin point class that lists all the plugins that adhere to that interface with a common dependency. Finally, we're able to utilize that plugin point to request a specific plugin and act against its APIs. In this version, I've added a generic A/B testing interface as a parameter required to construct the plugin point. So I've walked you through a bit of the high-level idea that the rib tree can attach and detach branches when needed. And of course, this implies that there are lifecycle-related methods that are being fired underneath. If there's creation and destruction, things getting garbage collected, and there's lifecycles in general being associated with ribs. I also mentioned that ribs uses Rx. We actually make very, very heavy use of Rx. And as many of you have probably guessed, this means that it can be very vulnerable to memory issues and leaks if cleanup isn't done properly. If you saw Johan and Ukarsh's talk yesterday, untangling your app, I think they walked into some really interesting scenarios around this. To address automatic unsubscriptions for Rx streams, we ended up creating a new library. And so that's called Autodispose. I think probably many of you have used this by this point. It's become pretty prevalent in the community. And it's a library to automatically manage your Rx subscriptions. So it holds onto scopes and it automatically unsubscribes based on lifecycle events. They could be custom or they could be the Android ones. You can kind of define this and configure it how you see. So the idea here is pretty simple. You construct your Rx chain like any other. And then before subscribing, you can simply call the static autodisposable method, which with one of 3 overloads for convenience. Then, so this is kind of broken apart into 3 different parts. The maybe semantic, which is modeled after take until, which takes an observable, and that emits a signal to signal completion of a lifecycle event. A lifecycle scope provider, which is an interface that exposes lifecycle events you can use to care about the signaling of this completion as well. This would be used to explicitly tie the subscription to the lifecycle event of another object. And the scope provider, which is an abstraction that allows you to allows objects to expose, control, and provide their own custom scopes. These all return an auto-dispose converter object that implements all the Rx converter interfaces so that you can use it with the as operator in RxJava. Also, auto-dispose exposes a lot more functionality to make it more powerful, including Kotlin extensions, Rx lifecycle extensions, adapters to plug into the Android architecture components, a plugin system modeled after RxJava's plugins, an error-prone checker, and much more. So be sure to check out the GitHub repo to get started with that. Another area that can be really challenging when dealing with dynamic app state tree is referencing a static snapshot of that entire tree. So a common area where we've seen this could be problematic is with deep links. The deep link, you have a string that's like a serialized reference to a state of your application, and you need to achieve that within this very dynamic tree that has a lot of state for the application. So to address this, we designed a framework that lives within the Ribs open source repo under a subfolder called workflows. This interops with Ribs, and it's a framework to describe reactive steps. The workflow is composed of 3 parts. The first is the step, which is a single action to be completed. The second is an actionable item, which is an interface representing the specific rib, the specific steps a specific rib can accomplish. And the last is the workflow class itself. Each one of these is expected to describe a series of steps required to achieve its end goal. Sorry. Here's an example diagram of a workflow handling a single sign-on deep link. So you have one app talking to another app to do authentication. So once the plugin point creates a specific workflow to handle the deep link based on its as applicable method, the workflow framework will then describe the number of steps needed to progress through the rib states here. Using a series of implemented steps on each actionable item, which I said is an interface to the specific interactor with a rib node, each interactor knows how to progress to its next state in the tree. We're able to navigate multiple ribs down to the single sign-on oriented one from root where this is attached and defined. Here's some code to handle the meat of that workflow. We have a series of steps defined that will walk root down to our main interactor before attaching a full screen rib. For example, in our root interactor, we define a step that waits until the user signed in and then triggers the next step. If the user is already signed in, this will trigger immediately. Otherwise, this will wait for the user to complete the sign-in or onboarding flow before it continues to the next step where it authenticates, generates an auth token to send that back to the calling application. So we've covered ribs and a variety of tools that help make them more usable. Let's move on to tools not as directly related. They're not quite in the same stack, but they're very useful for us. They've helped with productivity. Many of them are open sourced either by us or things that we use and contribute to. So as Android apps grow, providing common features and consistency across the UI elements becomes really challenging too. We have a number of teams building UI functionality, many designers that are working on different projects, and it's important to keep the app looking consistent for the end user. And more importantly, it's a priority to keep it behaving consistently. So to keep consistency for the user, we collaborated with our designers to create a style guide so that downstream teams, also we call them program teams, can consume this, and they can use this as a source of truth to reference what specific components should be looking like. Now, this solved one of our problems, but it introduces some others. First, since Android owns the view base classes, this often means that we're maintaining a large set of customized base views ourselves. So when a bug or feature is put into one, it must be copied and added to the others. So we'd like to get this resolved with things like Rx binding APIs, analytics in the views, accessibility automatically in the views, amongst many other things. We found that there was a lot of duplication. Second, as the organization grows, what ensures that the downstream engineers use the appropriate classes as opposed to creating custom UI? So to address the first point, we built and released a tool called Artist. It's on GitHub, again, the link's at the bottom. Artist is a Kotlin-based code generation tool that allows you to generate a base set of views in Android. Artist-generated views are created using a stencil and trait system. Each view type is declared with a single stencil, which is comprised of a set of traits. All of this comes together to create an easily maintainable system of stencils and traits. The stencil describes the view to be generated, and it has properties that can be configured on it directly. A trait has a hook into the stencil's code gen where you can implement specific pieces of functionality shared across multiple stencils. So this is where you would have your specific one for analytics or RX binding or whatever that might be. So here's a basic example of a trait. Here we want to create a convenience methods for checking the visibility state of a view. We'll iterate through the visible states and then create convenience is visible, is invisible, and is gone. And then for each of these, we'll use a tool like Java Poet to write the meat of the method. We take those and then we can code gen a view. And then we'll write up our stencil, specifying the view information to be generated as well as listing the traits that we want added. Now we can see what a generated view would look like from all that. For more information about Artist, as well as detailed instructions on wiring it up to your Gradle script, check out the public README. And we recently open sourced another library that works really well with Artist called Stylist. It's a pretty similar concept, but this works really well with Android themes, which we found to be pretty problematic in practice at scale as well. Uses a similar model of stencils and then what we call style items. We're able to define and generate multiple sets of themes with common functionality from different parents. For example, let's say you had a very rich theme and you had dark mode and light mode. You could output all of that here, and then you could maintain that in a much easier way. Stylist will create identical sets of themes from both parents, providing much greater maintainability as you develop and evolve your app. In addition to tools to generate the proper views and themes, we make extensive use of linting and reporting rules to give developers immediate feedback when they inappropriately use the Android views themselves, or they misuse one of our libraries, and just to generally help them avoid potential errors. Here we have a simple lint rule that extends the resource XML detector. When this discovers usage of the standard switch compat, it'll throw an error to the developer informing them that they should use our artist-generated foo switch instead. Secondly, we automatically add blocking reviewers in our code review process if certain behaviors are used or are adjusted using Herald, which is a part of the Fabricator tool suite. It's an open source code review tool that we use at Uber for managing our repositories. And it's a powerful part of our tool chain. As teams grow, it gives an automated way to being alerted or when folks make changes that you may not be aware of or that you may care about. In addition to the errors I mentioned, there are a slew of others that will impact large software projects. The larger the project grows, the more likely it is to be affected by common and avoidable errors. One tool that we use on our mobile projects is ErrorProne. It's a fast compiler plugin built by Google that will fail at build time with common errors and an easy-to-write checker API. For example, in this piece of code, we're injecting our object graph after we've called super.onCreate. Now, this can cause configuration change bugs and issues with reattached fragments that the system handles. So ErrorProne would halt the execution at compile time to let you know about the error and resolve it, as opposed to lint, which is checking after compile time, and developers can ignore the warnings as well. And ErrorProne makes it easy to write new checkers for error types as well. When we looked at the benefits of Kotlin and Swift, one obvious win was its handling of nullability, and how it throws that right in your face at compile time. So using ErrorProne as the base, we wrote and open sourced a tool called Nullaway, which is an extension. And this helps solve that billion-dollar mistake, and it brings first-class nullability to Java. It's fast, it can run on every build of your app, pretty little overhead. So here's a quick example of using Nullaway. We have a method that takes x and then prints it out. In this case, we are sending null. By default, Nullaway assumes all unannotated parameters are non-null. And at compile time, Nullaway will halt the build to alert us to the issue. And we can fix the issue by adding the annotation. However, now Nullaway would fail again on the printing usage unless we added a if null check as well. and then it understands that this is a non-null after the check, similar to Kotlin. At Uber, we combine error-prone with another validation tool that we've created called Rave. Stands for Runtime Annotation Validation Engine. Rave uses annotations already present on your data models to code-generate validators for dynamic data to ensure that it adheres to the contract that you expect at runtime in addition to compile time. So first, we need to create a validator factory. Here, the simple factory-generated validator is written once a model references the sample factory class using the validated annotation. So let's assume we have a model that's being hydrated from JSON on a network request. And we need to indicate if a match was made or not. So here we're defining a Rave factory class to generate the validator. We reference the factory we created, and we're being specific that the match variable is non-null, and that it must be one of the two states that we defined here. Now, when we indicate to Rave to validate this model, it'll use the validator to throw an exception if something is wrong. This would be easy to put into a retrofit adapter, and then efficiently validate models on every deserialization. Now, while Rave is powerful, and it works well when we have dynamic data that we're deserializing from JSON, I would definitely recommend you take an alternate approach when you're dealing with your network models, and use something that is more of a binary protocol. So use a tool like protobuf or thrift to have the same generated model on both the client and the server, and to guarantee states, and then have more efficient network traffic as well. These tools typically allow you to define language-agnostic spec and then generate class files for various code bases. For most of our main models and services now, this is what we use. We primarily generate everything using a stack built on top of Thrifty. Thrifty is Microsoft's mobile-focused Thrift compiler. Its compiler takes a similar approach to Square's Wire for protobuf, in that it generates a much smaller set of classes from the spec than the server generator would, so that it's more efficient with mobile. So lastly, as I said, this talk isn't really a deep dive into these tools today. It's kind of just putting them in your face, letting you be aware of these. Hopefully you can follow up with these later if you felt like any of the use cases would work for your application. And again, I think you should be very opinionated about your own scaling needs. If you don't need these, don't use them. So here's a list of all the projects that I covered today. And we're looking for contributors for all of these. We're pretty active in our own repos, and we do have a lot of external traffic, but we'd love to see more from the community. So please get involved. You can engage with us on the issues, the PRs, on Slack, on Twitter. We're in a lot of places. And many of my colleagues have done great deep dives into some of these topics. Many of them are here today. I believe Leland is giving a talk on Motif at 2 o'clock. So I think Gautam gave a talk yesterday on CI and monorepo and some of that related stuff. So watch those, attend those talks. You can follow up and watch these recorded talks. And of course, stay tuned for more open source software as we continue working on great projects. Thanks for attending today. I hope these provide some pointers for you to think about how you want to scale your own apps. If this sort of work interests you, my team is hiring. We do a lot of platform-oriented work. We support all of the mini apps that Uber builds. We have a booth right outside where we have a bunch of folks to talk about our different open source projects. If you want to kind of have a discussion around what your specific needs are, we'd be more than happy to chat. And I'll be out there to take questions after the talk. Thank you.